Logic gates. Logic gates are the basic building blocks of digital circuits. They provide the physical implementation for the mathematical operations of Boolean algebra. We have talked before about the AND logic gate and the OR logic gate and the inverter. Today we are going to talk about some other logic gates, namely the NAND gate, the NOR gate, the exclusive OR, and there is one more, which is the exclusive NOR gate. Okay, the NAND gate is the complement of the AND gate. It is an AND gate followed by an inverter. It is an AND gate followed by an inverter. This bubble here is the invert of the AND. So this is the symbol for the NAND gate. This is one symbol for the NAND gate. Of course, the output of this AND gate is A ANDed with B, all complemented. A ANDed with B, the complement, which is this one. Actually, this one, if we apply De Morgan's theorem, this is equal to A bar ORed with, this is equal to A bar ORed with B bar. So another symbol for the NAND gate is the negative OR. It's an OR gate between the two negative variables, A bar and B bar. So this is the NAND gate, and this is the truth table for the NAND gate. It's the complement of the AND. Another gate is the NOR gate. The NOR gate is the complement of the OR. This is an OR gate and followed by an inverter. This is another symbol for it, or the main symbol for the NOR gate. It's an OR followed by this bubble, which resembles an inverter. Of course, the output of the NOR gate is equal to A or B complement. Applying the De Morgan's theorem, this is equal to A bar ANDed with B bar. So another symbol for the NOR gate is the negative AND. If we put A bar here and B bar here, we put A here, and that means that A is complemented. This bubble here tells you that A is complemented before it goes as an input. And if we put B here, then the complement of which is an input to this gate. So this is the output of the NOR gate, the negative NOR. And this is the truth table for it. It's equal to 1 only if A and B are both zeros. So this is the complement of the OR. The exclusive OR gate is a different gate. This is the symbol for the exclusive OR gate. It is an OR gate as a symbol with this one, this arc is added. And the output, we write it as A exclusive OR with B. This is equal to A bar ANDed with B, which is this, ORed with A ANDed with B bar. This here is minterm number 1. And this here is minterm number 2. This is the truth table. This is minterm number 1, and this is minterm number 2. This gate is called the OR gate, or the OR function. Notice that the output is equal to 1 if one of the two inputs is equal to 1. The output is equal to 1 if one of the inputs is equal to 1. So it is called the OR function. Now the question is, can we expand the inputs at the exclusive OR gate? So can we have a gate with 3 inputs? Before we answer this question, let's look at these two circuits. Are these two circuits equivalent? In order for these two circuits to be equivalent, that means the output here must be equal to output here. And what is the output here? It is equal to the output of this one, which is X exclusive OR with Y, which is this. And the whole thing is exclusive OR with Z. Exclusive OR with Z. And this one, Y exclusive OR with Z. And before that, it is exclusive OR with X. If we prove that this expression here is the same as this one, that means these two circuits are equivalent. Let's see if these two expressions are equivalent. This part on the left-hand side is equal to this on the right-hand side. We do this by expanding this term, X exclusive OR with Y. This is equal to this, okay, and exclusive OR with Z. Okay, we do the exclusive OR here. We take the complement of the first term, which is this one, ANDed with the second, which is Z, ORed with this term, which is this, ANDed with the complement of the second term, which is this. Okay, here we take the Z inside, so we get this, and we take the Z inside and we get this. On this part, we take the complement here inside, so we get this, and this OR becomes an AND, and the complement of this one as shown, and this is Z. Now, we take this complement inside, so we get X instead of X bar. This AND here is ORed, and this is the complement. This AND goes down here. We take this complement inside, so this is X bar or Y, and this is Z. We take the Z inside this, so this is X ANDed with Z, or Y bar ANDed with Z. And this end goes here, and this here goes down here. The rest here stays the same. Now, we take the X bar inside this one. So this is X dot Z dot X bar, or Y bar dot Z ANDed with X bar, and or Y ANDed with X and Z, Y ANDed with X and Z, or Y ANDed with Y bar and Z, Y bar and Z. Okay, here we see X ANDed with X bar. This is 0, so this term goes out. And here we see Y bar ANDed with Y, so this term also goes out. We are left with this term, and this term, and this term, and this term. And this here is minterm 7, which is this. And this here is also minterm 2, if you add minterm 2. This one here is term 1. This is minterm 2, and this is minterm 4, and this here is minterm 7. So we are left with these expressions here, M1, M2, M4, and M7. Let's take a look at the right-hand side of the equation. X exclusive OR with Y, exclusive OR with Z. If we follow the same procedure in manipulating this expression, we will come up with the same answer for the left-hand side. Mainly, this is equal to M1, M2, M4, M7. You can try that out yourself. So from this, we see that these two circuits are equivalent. That means that I can put an exclusive OR gate in this form. Having 3 inputs, and the output is equal to X exclusive OR with Y exclusive OR with Z. And this is the truth table for these three circuits, equivalent circuits. This is minterm 1, minterm 2, minterm 4, minterm 7. Remember that we said that the exclusive OR is the odd function. Look at the output here. It is equal to 1. The number of ones here at the input is odd. It's equal to 1 here at the output. The number of ones here is odd. Here, the number of ones is odd. Here, we have 3 ones, which is an odd number. So the output is equal to 1. That's why it's called the odd function. Now, there is a gate called the exclusive NOR. The exclusive NOR is the complement of the exclusive OR. It's an exclusive OR followed by an inverter. Okay, what is this equal to? It is equal to A bar ANDed with B bar ORed with A, B. And this here is minterm 0. This here is minterm 3. This is minterm 0 and this is minterm 3. Also, we can say that the output of this gate, exclusive NOR, is the max terms, is the product of the max terms, M1 ANDed with M2. It's where the output is equal to 0. These are the max terms. This is the even function. Look, the output here is equal to 1 if the inputs are equal. It is equal to 1 if the inputs are equal. That's why it's called the even function. Here, the number of ones at the input is even. And here, the number of ones at the input is also even. Now, can we expand the number of inputs to the NOR gate? Let's see. Can we have a 3-input NOR gate? In order to have this, that means that the output of this circuit must be equal to the output of this circuit. Let's try to find out here. Output of this circuit is X ORed with Y complemented, and the output here is equal to this ORed with this complemented. Okay, and this will result in X or Y ANDed with Z bar. The output is X bar ANDed with Y or Z, and the output of this gate, X or Y or Z complement. So we see that the outputs are not the same. This output is not as this output is not as this output, so we cannot have more than 2 inputs NOR gates. They are not equivalent circuits. Okay, given this circuit, what is the output of this circuit, F4? How do we analyze this circuit to find out the output? We start from the input side of the circuit. What is the output of this AND gate? It's equal to A bar, B bar. Now, what is the output of this NOR gate? It is equal to A bar, B bar, ORed with C. And then the output F4 is the complement of that, which is equal to A bar, B bar complemented, ANDed with C bar, and this is equal to A or B ANDed with C bar. Again, what is the output of this circuit? We do that by analyzing the circuit starting from the input side. The output here is equal to XY. The output here is YZ. And the output, final output F is equal to the sum of these two terms. What is F here? We find the output here, which is AB. The output here is B, C, D, and the output here is the sum of these two terms.